There's a sound in the data that shouldn't exist, and scientists say the 3i atlas activated at Earth's atmosphere, a rhythm, a pulse. Something astronomers are calling a heartbeat, though they won't say it too loudly in official channels, because heartbeats imply life, or at the very least mechanism, and the object racing away from us right now, the one we've been calling 3i atlas, isn't supposed to have either. Let me take you back 24 hours, December 19th, 2025. The date itself feels ordinary until you realise what happened. An interstellar visitor, a chunk of matter that formed around a star we'll never see, in a system we'll never visit, passed within 168 million miles of Earth. Close by cosmic standards. Close enough that every major telescope on the planet and in orbit turned to watch. Close enough that we could actually measure it, analyse it, try to understand what it was made of and where it came from. And then it kept going. Right now, as you're reading this, 3i Atlas is already 270 million kilometres away. That's roughly twice the distance between Earth and the Sun, and it's moving fast. Not comet fast, not even escape velocity fast, hyperbolic fast. 58 kilometres every single second. At that speed, it will cross Neptune's orbit within a year, and then silence. Gone forever into the void between stars, carrying with it answers to questions we're only now learning to ask. But here's what's keeping scientists awake tonight. Here's what's flooding our data servers and breaking our models and making even the most conservative astronomers pause before they speak. The object isn't behaving like it should. Comets, we thought we understood. Ice and rock, dirty snowballs from the edge of the solar system, predictable in their chaos. They heat up near the sun, they outgaze, they develop tails, they sometimes break apart. Simple physics. Solar radiation does the work. 3i Atlas is doing something else entirely. The brightness fluctuations started almost immediately after closest approach. Not the gradual dimming you'd expect as an object moves away from our observation point. Not the random flickering of tumbling rock catching sunlight at different angles. This was rhythmic, intense, a pattern so precise that the first astronomers to notice it thought their instruments were malfunctioning. But the signal appeared in Chile, then Hawaii, then the orbital telescopes confirmed it. Different instruments, different locations, same impossible result. The object is pulsing. Picture this. You're watching something that should be getting dimmer as it recedes into darkness. Instead, it's getting brighter in waves. Spikes of luminosity followed by dimming over and over like a lighthouse beam sweeping across the void. Like something is turning on and off. Like something is breathing. The technical term is photometric oscillation. The colloquial term, the one slipping into conversations in observatory, cafeterias and late-night Slack channels, is the heartbeat. Because that's what it looks like when you graph it. A pulse. A living rhythm in something that has no business being alive. Standard cometary physics doesn't account for this. When a comet moves away from the sun, sublimation decreases. The ice stops turning to gas. The activity winds down. You get a tail that fades, a coma that dissipates, an object that returns to dormancy until its next pass through the inner system, if it even has a next pass. But 3i Atlas, already racing away from the warmth of our sun, is intensifying. The pulses are getting stronger. The pattern is becoming more defined. It's as if the object waited until we were watching to really turn itself on. What could cause that? If this were a natural body, a simple ball of ice and dust held together by its own weak gravity, the brightness spikes would need to come from rotating active regions. Imagine a vent or a crack on the surface, a place where volatile ices are exposed to vacuum. As the object spins, that vent rotates into view, catches sunlight, erupts in a jet of gas and dust, and creates a temporary brightening. Every rotation, another pulse. That's plausible. That's within the bounds of known physics, except the rotation would need to be incredibly regular. Comets tumble, they wobble. Their spin axes precess under the influence of uneven outgassing. You might get periodic brightenings, but they'd be messy, irregular, damped over time as the object loses mass and changes shape. What we're seeing is clean, mathematical. The period is consistent to within fractions of a percent. The amplitude barely varies. It's the kind of signal you'd expect from a gyroscope, not from a crumbling snowball. And then there's the intensity problem. For the pulses to be this bright, this far from the sun, the outgassing would need to be extraordinarily violent. We're talking about explosive venting, pressurized reservoirs of exotic ices suddenly finding release. The energy budget doesn't close easily. The amount of solar heating at 1.8 astronomical units, where 3i Atlas is now, shouldn't be enough to drive this kind of activity. Not continuously, not with this kind of power, unless something else is providing the energy. That thought is dangerous. That thought leads down paths most scientists don't want to walk. Because if solar heating isn't enough, you need an internal source. Radioactive decay, maybe. Tidal heating from rapid rotation or structural stress. Or something we haven't considered. Something we don't have a name for yet. The heartbeat is just the symptom. The real mystery lies in what's causing it. And to understand that, we need to look at what this object is actually made of. We need to examine the blood of the comet. Before we go deeper, before we unpack the chemistry that's rewriting textbooks and the physics that's defying models, I need you to understand something. This story is happening in real time. Right now, as 3i Atlas speeds toward the outer solar system, observatories across the planet and beyond are collecting data. Spectra are being analysed, images are being processed, trajectories are being refined. Every day brings new information. Every night brings new questions. If you want to stay ahead of this, if you want to understand what we're actually witnessing here, make sure you hit that subscribe button, turn on notifications. Because this isn't just a documentary about something that happened. This is an investigation into something that's happening right now, and the conclusions we reach in the next few weeks might fundamentally change how we see our place in the galaxy. The official position, the one you'll hear from NASA and ESA and every major space agency, is calm and measured. There is no threat. The flyby was safe. The object is leaving. Everything is under control. And technically that's true. 3i Atlas never posed a collision risk. Its trajectory was calculated weeks in advance. We knew it was coming. We knew where it would go. We knew it would pass harmlessly and continue on its way. But that official calm is deceptive. Because while the trajectory was predictable, the behavior of the object itself has been anything but. The heartbeat is just the beginning. As we peel back the layers, as we examine the spectroscopic data and analyse the morphology and trace the orbital mechanics, we're finding contradictions everywhere. Things that don't fit. Things that shouldn't exist together in the same object. Let me give you a preview of what's coming. Because the heartbeat, as strange as it is actually the least troubling anomaly. The spectroscopic readings, the chemical fingerprints captured as sunlight passes through the gas surrounding the nucleus show unexpected spikes. Carbon dioxide at levels far higher than any comet in our solar system. Methanol in quantities that suggest a formation environment radically different from our own Kuiper belt. And then there's the nickel. In our solar system, in every meteorite we've studied, in every asteroid we've analysed, nickel always appears alongside iron. They're cosmic twins, forged together in stellar furnaces, distributed together in the dust that builds planets. You find one, you find the other. It's a rule so fundamental we barely think about it anymore. 3i Atlas is showing strong nickel signatures with almost no iron. That shouldn't be possible. Not naturally. Not without a refining process, a separation mechanism operating on a scale and with a precision we don't have a model for. It's as if someone took a planetary core, extracted just the nickel, and sent it on a billion-year journey through the galaxy. And then there's the tail, or rather the anti-tail. Every comet diagram you've ever seen shows the tail pointing away from the sun. That's basic physics. Solar wind, the stream of charged particles flowing outward from our star, pushes gas and dust backward like a windsock in a gale. The tail always points away, always. 3i Atlas has a prominent stream of material pointing toward the sun, not a perspective trick, not an optical illusion from viewing angle. Multiple observations from different positions confirm it. There is actual material moving sunward, fighting against the solar wind, maintaining a narrow, focused beam over millions of kilometers. A collimated jet, in technical terms. The kind of structure you see in black holes or young stars with powerful magnetic fields. Not in comets. For a jet to maintain that kind of focus, that kind of directionality, over that kind of distance, you need a focusing mechanism. You need something to confine the flow, to prevent it from spreading out the way gas naturally wants to spread in vacuum. Nature can do this, under specific conditions. But the conditions required are extreme, improbable, difficult to reconcile with what we think we're looking at, unless we're wrong about what we're looking at. I want you to think about what happens when too many impossibilities stack up. 1 anomaly is interesting, 2 anomalies are puzzling, 3 anomalies are concerning. But when you start cataloguing 5, 10, 15 distinct contradictions to the standard model, when every new measurement seems to deepen the mystery rather than resolve it, you reach a point where you have to ask a harder question. Are we looking at a natural object behaving in ways we don't understand? Or are we looking at something else entirely, something we've been assuming can't exist because we've never seen it before? That question has split the scientific community down the middle. On one side, the conservatives, the majority, the researchers who believe that exotic natural explanations, however improbable, are always preferable to the alternative. They argue that we're witnessing an ancient object, possibly billions of years old, formed in a stellar system with different chemistry and different physics than our own. They point to the detection of water vapour and carbon monoxide alongside the anomalous signatures as proof that this is still, fundamentally, a comet. Just a weird one. A really, really weird one. On the other side, a smaller but increasingly vocal group led by Harvard astrophysicist Avi Loeb argues that we're trying too hard to fit a square peg into a round hole. They say we're inventing increasingly complex natural scenarios to explain away features that would be trivial to explain if we allowed for the possibility of artificial origin. They look at the heartbeat and see a rotating mechanism. They look at the nickel and see material selection. They look at the collimated jet and see a thruster. Loeb has compiled a list of 15 specific anomalies, 15 distinct ways in which 3I Atlas contradicts what we expect from a natural interstellar comet, and he's arguing, publicly and persistently, that we need to at least consider the hypothesis we've been avoiding, that this might be a piece of extraterrestrial technology, a probe, a derelict spacecraft, a fragment of something built by minds that aren't human. Now, before you dismiss that as science fiction, before you write it off as sensationalism or clickbait, I want you to consider the stakes. Because this isn't about belief or wishful thinking. This is about methodology. This is about how we approach the unknown. If we assume a priori that every object we detect must be natural, we will never recognize artificial when we see it. We'll invent increasingly baroque explanations to preserve our assumptions. We'll miss the signal in our desperation to maintain the noise. But if we're too eager to see artificiality, if we jump to conclusions based on incomplete data, we make fools of ourselves. We undermine the credibility of the entire field. We become the researchers who cry alien at every unusual asteroid, and soon nobody listens anymore. The balance is delicate. The stakes are enormous. Because 3I Atlas isn't the first interstellar visitor we've detected, it's the third. And each one has been strange in its own way. Each one has challenged our models. Each one has forced us to expand our understanding of what's possible. Oumuamua, the first one, back in 2017, was cigar-shaped and tumbling and accelerating in ways that outgassing couldn't fully explain. Loeb proposed it might be a light sail, and the scientific establishment largely dismissed him. But 8 years later, we still don't have a consensus on what Oumuamua actually was. Tussos I Borisov, the second one, in 2019, looked more like a normal comet. That was almost a relief. Proof that most interstellar objects are probably just rocks and ice, nothing exotic, nothing to worry about. And now 3I Atlas arrives with its heartbeat and its nickel and its impossible tail, and the questions come flooding back. What are we really seeing out there? What's normal and what's extraordinary? And how would we even know the difference? The thing is, we're not equipped for this. Humanity has been studying comets for thousands of years, but we've only been studying interstellar comets for 8 years. We have a sample size of 3. 3 objects, each observed briefly as they raced through our solar system and vanished back into the dark. We're trying to build a taxonomy from 3 data points. We're trying to understand a population from a sample that wouldn't qualify for a basic statistics class. Every assumption we make is provisional. Every model we build is based on extrapolation from local experience. We're like islanders who've never seen the mainland trying to understand continental geology from the driftwood that washes up on our shores. Sometimes the driftwood is just driftwood, but sometimes, maybe, it's a piece of a ship. The heartbeat continues as we speak. 58 kilometers per second, 3I Atlas is putting distance between itself and everything we can bring to bear to study it. Our best telescopes are tracking it, trying to squeeze every photon of information from its fading light. But there's a limit to what we can learn from this distance, a limit to what spectroscopy and photometry can tell us. What we need is to get close. What we need is a spacecraft intercept, a probe that can match velocity with this thing and examine it up close with instruments that can resolve surface features and measure magnetic fields and sample the gas directly instead of analysing it from millions of miles away. We had plans for this. The European Space Agency's Comet Interceptor mission, designed exactly for this scenario. A spacecraft parked at a gravitationally stable point, waiting for a long-period comet to appear, ready to launch an interception on short notice. It's scheduled for 2029. 4 years too late. 3i Atlas slipped through the net. We saw it coming, we tracked it, we analysed it, but we didn't have the capability to chase it. And now it's leaving, carrying its secrets with it, and all we can do is watch the data come in and try to make sense of the impossible. Unless we do something desperate. There's a concept called Project Lyra, a theoretical mission architecture designed specifically to chase down interstellar objects using advanced propulsion and gravitational assists. The idea is to use Jupiter's massive gravity well as a slingshot, to accelerate a probe to velocities that would normally require fuel loads we can't lift off Earth. Nuclear thermal propulsion, maybe. Solar sails pushed by ground-based lasers, perhaps. Technologies that exist on paper but haven't been deployed at scale. The math is brutal. To catch 3i Atlas at this point, a probe would need to launch within weeks. It would need to achieve delta-V values that push the absolute limits of our current engineering. And even then, it might only catch up when the object is so far from the sun that solar panels won't work and instruments would need to operate in near-total darkness on battery power or radioisotope generators. But some scientists are arguing we should try anyway, because if there's even a chance that Loeb is right, if there's even a possibility that we're watching a piece of technology drift past us, then the cost of a failed intercept mission is trivial compared to the cost of missing our one shot at confirmation. Think about what that would mean. Physical contact with artificial technology from another star system. The materials science alone would be revolutionary. The propulsion systems, even if defunct and ancient, would teach us things about physics we haven't discovered yet. The computer systems, if they exist, might contain data about the builders, their homeworld, their journey across the galaxy. Or we'd find a lump of weird ice and rock and confirm that our solar system isn't special, that comets form in lots of different ways under lots of different conditions, and sometimes the chemistry and physics conspire to create something that looks almost, but not quite, artificial. Either answer would be valuable, but only one of them would be transformative. The problem is political and financial as much as technical. Space agencies don't pivot quickly. Budgets are allocated years in advance. Missions are planned in committees and approved by governments and scrutinized by review panels. The idea of a rapid response intercept, of green-lighting an entire spacecraft program on the basis of ambiguous data from a single object, is almost unthinkable within the current framework. Almost. There are rumours, unconfirmed, that private space companies are looking at the problem, that wealthy individuals with an interest in the search for extraterrestrial intelligence are having quiet conversations with aerospace engineers about what it would cost to put together an intercept mission on a compressed timeline. That somewhere, in a facility not bound by government bureaucracy, people are doing the math and building the hardware just in case. I can't verify those rumours. But I can tell you that the window is closing. Every day that passes makes the intercept harder, more expensive, less likely to succeed. Within a few months, it will be functionally impossible. 3i Atlas will be too far, moving too fast, and our ability to reach it will vanish, and then we'll be left with what we have now. Terabytes of data, thousands of images and spectra, measurements of brightness and composition and trajectory, the pieces of a puzzle that we might spend decades trying to solve. The heartbeat will fade, the signal will drop below the noise threshold, and the object will continue its journey across the galaxy, indifferent to our questions, unconcerned with our theories, a mystery that passed through our neighbourhood and left us wondering. But before it fades completely, before we lose the ability to observe it at all, we need to extract every piece of information we can. We need to understand what we're looking at, and to do that, we need to examine the chemistry in detail. We need to look at what this thing is actually made of. Because the heartbeat is just the symptom, the chemistry is the disease, or the diagnosis, depending on what we find when we analyse the blood of the comet. Think of spectroscopy as reading a fingerprint made of light. When sunlight hits the gas cloud surrounding 3I Atlas, the atoms and molecules in that cloud absorb specific wavelengths and emit others. Every element, every compound has its own unique signature. By spreading the light into a spectrum and measuring which wavelengths are missing or enhanced, we can identify exactly what's there. It's like reading a barcode that tells us the chemical composition of an object millions of miles away. We've used this technique on thousands of comets. We know what a normal solar system comet looks like chemically. Lots of water vapor, carbon dioxide and carbon monoxide in modest amounts, traces of ammonia and methane, simple organics, dust particles made of silicates and carbon compounds. Nothing exotic, nothing that would make you do a double take at the data. The spectra from 3I Atlas make you do a triple take. First, the carbon dioxide. It's not just present, it's dominant. The ratio of CO2 to water is far higher than anything we've seen in our local comets. In most solar system comets, water is the star of the show. It's the primary volatile, the stuff that drives activity and creates the visible coma. Carbon dioxide is a supporting player, interesting but secondary. In 3I Atlas, the roles are reversed. Carbon dioxide is the primary outgassing species, with water almost relegated to trace status. That tells us something profound about where this object formed. Carbon dioxide ice is stable at lower temperatures than water ice, but requires a specific thermal environment. The object must have formed in a region of its parent star system that was significantly colder than our Kuiper belt, or the chemistry of that system was fundamentally different from ours, with carbon dioxide more abundant in the primordial disk that formed planets and comets. Either way, it's a window into a stellar system we'll never visit, a snapshot of conditions light years away, frozen in time and delivered to our doorstep. Then there's the methanol, in high abundances, far beyond what we'd expect. Methanol is an alcohol, a simple organic molecule that's a building block for more complex chemistry. In the context of astrobiology, it's interesting because it's a precursor to the kinds of molecules that life uses. Finding it in a comet isn't surprising. Finding this much of it is. The quantities suggest that wherever 3I Atlas formed, organic chemistry was robust. The conditions favoured the synthesis of complex carbon-based molecules. If you were looking for signs that other stellar systems can produce the chemical precursors to life, this would be encouraging evidence. But then we get to the nickel, and this is where the story goes from unusual to genuinely troubling. In every meteorite we've studied, in every asteroid we've analysed, nickel and iron appear together. They're produced together in supernova explosions, the violent deaths of massive stars that forge heavy elements and scatter them across space. They condense together in the cooling material that forms new stellar systems. They're chemically similar enough that they mix readily, forming alloys that are stable and common throughout the cosmos. Where you find nickel, you find iron. It's one of the most reliable rules in cosmochemistry, except 3I Atlas is breaking it. The spectroscopic signatures show strong emission lines from nickel vapor. Not trace amounts, not borderline detections that might be noise or instrumental artifacts. Clear, strong signals indicating substantial quantities of nickel in the gas being released from the nucleus, but the corresponding iron lines, the ones that should be just as strong or stronger, are almost absent. How do you separate nickel from iron on this scale? How do you create an object that's enriched in one but depleted in the other? Naturally it's possible, but requires very specific conditions. You'd need a differentiated body, a planetesimal or protoplanet that was large enough and hot enough to separate into layers based on density. Iron, being slightly denser, would sink toward the core. Nickel, being slightly less dense, might concentrate in a layer above. If that body were then catastrophically disrupted, torn apart by a collision or tidal forces, you might get fragments that represent different layers. A chunk of the nickel-rich layer could, in theory, exist as a separate object. But even that scenario has problems. The separation wouldn't be perfect. You'd still expect to see significant iron alongside the nickel, and the disruption event would need to be violent enough to shatter a planetesimal, but gentle enough that the fragments remain coherent. It's possible, but it requires threading a very narrow needle of circumstances. The alternative explanation, the one that some researchers are whispering about in private conversations but won't put in papers yet, is that the nickel signature indicates something other than natural geological processes. Nickel alloys are used in engineering. They're corrosion resistant, they maintain strength across a wide temperature range, they're relatively easy to work with compared to pure metals. If you were building something designed to survive the harshness of interstellar space, to endure radiation and micrometeorite impacts and thermal cycling over millions of years, nickel alloys would be an excellent material choice. I'm not saying that's what we're looking at. I'm saying the data is consistent with that interpretation, and the absence of iron makes the natural explanations increasingly convoluted while the artificial explanation remains straightforward. Occam's razor suggests we should prefer the simplest explanation. But how do you define simplest when one explanation requires exotic geology and improbable cosmic accidents, while the other requires accepting that we're not alone in the universe? The chemistry doesn't just tell us about composition, it tells us about activity. The fact that we're detecting these volatile species at all means they're being actively released. Ice is sublimating, gas is escaping, the object is not inert, and the pattern of release, the way different chemicals appear and disappear in the spectra over time, gives us clues about surface processes. What's puzzling is the intensity. 3I Atlas is relatively far from the Sun now, moving outward, entering regions where solar heating should be minimal. And yet, the outgassing continues. In fact, it seems to be intensifying in pulses, those same pulses that create the heartbeat we discussed earlier. That requires energy. More energy than passive solar absorption should provide at this distance. Either the object has an internal heat source, something generating warmth from within, or it's extraordinarily efficient at absorbing and storing solar energy. All the volatiles are so reactive that even minimal heating triggers vigorous release. Each possibility has implications. Internal heat could mean radioactive decay, tidal heating from rotation, or some process we haven't identified. Efficient energy storage might indicate materials or structures we're not familiar with. Hyperreactive volatiles would suggest chemistry from a stellar system with very different conditions than ours. None of these explanations are fully satisfying. Each one raises new questions, and then there's the anti-tail, the feature that defies basic physics and refuses to go away, no matter how many times we check the data. Comet tails point away from the Sun. This isn't complicated. The solar wind, that stream of charged particles constantly flowing outward from our star, pushes gas and dust backward. Radiation pressure from sunlight does the same thing. The result is a tail that always extends in the anti-solar direction, away from the Sun, regardless of which way the comet is actually moving. You can see this with any bright comet. The tail doesn't trail behind like exhaust from a rocket. It points away from the Sun. A comet approaching the Sun has its tail behind it. A comet moving away from the Sun has its tail in front of it. The orientation is determined by the Sun's position, not the comet's motion. 3I Atlas has a structure extending toward the Sun. A narrow, focused stream of material moving in the wrong direction. Multiple observations from different viewing angles confirm it's not a perspective effect. There's actual material moving sunward. For that to happen, the material needs to overcome the solar wind. It needs force. That means either the particles are too massive to be easily pushed, perhaps large grains of that mysterious nickel we keep detecting, or they're being ejected with significant velocity in that specific direction. But here's the critical detail. The anti-tail isn't a spreading cloud. It's collimated. It's a beam. Over millions of kilometers, it maintains a narrow profile without dispersing the way gas normally disperses in vacuum. In astrophysics, we see collimated jets in extreme environments. Black holes produce them through powerful magnetic fields that confine infalling material into tight streams. Young stars create them as they accrete mass from their surrounding disks. Pulsars emit beams of radiation along their magnetic poles. These are high-energy, high-field phenomena. They require mechanisms that simply shouldn't exist on a comet. A comet is small. Its gravity is negligible. It has no significant magnetic field. There's no mechanism, no natural structure that would allow it to focus a jet of gas and dust into a beam that remains coherent over interplanetary distances. And yet, there it is, in the data, confirmed by multiple instruments, a sunward-pointing, collimated stream of material that violates our understanding of how comets work. Some researchers are trying to model it as a perspective effect we're misinterpreting. Others suggest it might be a dense filament of dust caught in the comet's orbital plane, backlit by the Sun in a way that creates the illusion of sunward motion. But the geometry doesn't support these explanations. The viewing angles were carefully calculated. The positions of Earth, the Sun, and the comet at the time of observation don't create the conditions needed for a perspective trick, which leaves us with the possibility that the anti-tail is real, that there is actual material moving toward the Sun, powered by something other than normal cometary outgassing. If the object is rotating, which the heartbeat suggests, and if it has a specific vent or nozzle that happens to point sunward at certain points in the rotation, you could get directional ejection. But for that ejection to be powerful enough to overcome solar wind and radiation pressure, and for the jet to be stable and collimated, the nozzle would need to be remarkably well defined. A jagged crack in ice produces a messy spray, a precise opening produces a beam, and the energy requirements are substantial. You'd need pressure, a reservoir of volatile material under enough stress that when released, it shoots outward with enough velocity to fight against the solar wind. That implies internal structure, chambers or cavities where pressure can build, material strong enough to contain that pressure until the right moment. Natural comets can have internal voids. Sublimation below the surface can create cavities. But the precision required for a stable, collimated, sunward-directed jet pushes the boundaries of what we'd expect from random geology. This is where Avi Loeb enters the conversation with full force, because he's looking at the same data everyone else is seeing, but he's asking a different question. Instead of asking, how can we make this fit into natural processes, he's asking, what would this look like if it weren't natural? And the answers he's getting are uncomfortable. The nickel without iron looks like material selection. The collimated jet looks like a thruster or a controlled vent. The heartbeat looks like rotation of a structured object with asymmetric features. The precise trajectory through the solar system, threading past multiple planets without capture or collision, looks like navigation. Loeb has compiled his list of 15 anomalies, 15 specific data points that, individually, might be explained away, but collectively paint a picture that's difficult to reconcile with a dirty snowball from another star. He's not saying with certainty that 3I Atlas is artificial. He's saying we can't rule it out, and he's saying that the burden of proof needs to be on those claiming. It's natural, because at some point when you've stacked up enough impossibilities, the null hypothesis shifts. The scientific establishment pushes back hard. They point to the detection of water vapour and carbon monoxide. They point to the X-ray flares observed during the flyby, which occur when solar wind interacts with cometary gas, and are a known signature of natural cometary activity. They argue that all the anomalies, however unusual, are still within the realm of extreme but natural comet behaviour. They emphasise that extraordinary claims require extraordinary evidence, and a few odd spectral lines, a weird tail geometry, some unusual acceleration. These aren't enough to overturn the default assumption that what we're looking at is a natural object. But even the skeptics admit that some of the features are hard to explain. The stable collimated jet, in particular, is a puzzle that doesn't have a good natural solution yet. It's the crack in the armour, the anomaly that refuses to be explained away. And that brings us to a fundamental question about how we approach the unknown. Because science is conservative by design, we prefer explanations that fit within established frameworks. We resist paradigm shifts because most of the time the paradigm is correct and the anomaly is just incomplete data or misunderstood physics. But sometimes the paradigm is wrong. Sometimes the anomaly is real. And if we're too committed to the old model, we miss the new reality entirely. The history of astronomy is full of examples. Continental drift was rejected for decades because the mechanism seemed impossible. Meteorites were dismissed as folklore because rocks don't fall from the sky. The expansion of the universe was initially resisted because the cosmos was supposed to be static and eternal. In each case, mounting evidence eventually forced acceptance. But there was a period, sometimes years or decades, when the data was pointing toward a new understanding, and the scientific community was fighting to preserve the old one. Are we in one of those periods now? Is 3I Atlas the data point that should be shifting our paradigm? Or is it just a weird comet that we'll eventually understand once we refine our models? I don't know, and that's the honest answer. What I do know is that the chemistry is strange enough to warrant serious attention. The nickel without iron is a legitimate puzzle. The anti-tail is a legitimate anomaly. And dismissing these things as mere curiosities might be a mistake. Because if Loeb is even partially right, if there's even a small possibility that we're looking at technology instead of geology, then the implications are staggering. It would mean we're not alone. It would mean that other civilizations exist or existed, that they built things capable of crossing interstellar space, and that the galaxy might be filled with their artifacts, their ruins, their active probes, just waiting for someone to notice them. And if we're not looking, if we've decided in advance that everything must be natural, we'll never see them. We'll catalogue them as asteroids and comets and move on, blind to the most important discovery humanity could ever make. The heartbeat continues, the chemistry confounds, the anti-tail persists, and 3i Atlas races away from us at 58 kilometers per second, carrying answers we desperately want and might never get. The clock is ticking, the data is accumulating, and somewhere in the numbers, in the spectra and the light curves and the orbital calculations, there's a truth we haven't uncovered yet. The question is whether we'll figure it out before the object fades from view and the opportunity vanishes forever. The question is whether we're brave enough to consider possibilities that terrify us. The question is what we're willing to believe when the impossible becomes the only explanation that fits. The blood of the comet has been analysed. The chemistry is wrong, the physics is broken, and we're running out of time to understand what that means. But there's more to this story than just chemistry and trajectories. Because while scientists argue over spectral lines and jet collimation, the rest of the world is watching, and their reactions tell a different story. A story about fear and hope, and the desperate human need to find meaning in the void. The cultural response to 3i Atlas has been as volatile as the object itself, and in that response, in the way governments and media and ordinary people are processing this visitor, we might find clues about what it really means to encounter the unknown. Because the science is one thing, the human reaction is another, and sometimes the reaction tells you more than the data ever could. The world is watching 3i Atlas, and what they're seeing isn't just a comet. It's a mirror reflecting back our deepest anxieties and our highest aspirations. It's a Rorschach test written in starlight and ice, and the interpretations are all over the map. Some see a weapon, some see a god, some see a machine, and some, desperately, see nothing at all, because acknowledging the strangeness would mean confronting possibilities they're not ready to face. In Russia, at a press conference on December 19th, President Vladimir Putin made a joke that landed with a thud. He called 3i Atlas a secret weapon of Moscow, then quickly laughed it off, assuring reporters that it's just a comet from another galaxy, hundreds of millions of kilometers away, nothing to worry about, our scientists know exactly what it is. The room laughed, but the joke revealed something. The fact that he felt the need to address it at all, even in jest, suggests that somewhere in the corridors of power, people are asking questions. Is this a threat? Could it be controlled? Should we be worried? The Russian Space Agency has been notably quiet about their own observations. No published data, no spectroscopic analysis shared with the international community. That's not unusual for early-stage observations, but it's also not typical for an event of this magnitude. Usually there's cooperation. Data gets shared. Everyone benefits from collective analysis. The silence suggests either they're seeing the same things everyone else is and don't want to draw attention to the anomalies, or they're seeing something different and don't want to reveal what they know. In the United States, NASA has been careful to maintain a posture of calm scientific interest. Their official statements emphasize the safety of the flyby, the value of the observational data, and the excitement of studying our third interstellar visitor. They acknowledge the unusual features, the high carbon dioxide ratio, the photometric oscillations, but frame them as opportunities to expand our understanding of cometary diversity. They don't use the word heartbeat. They certainly don't entertain speculation about artificial origins. The message is controlled, measured, designed to inform without alarming. Behind the scenes, though, there's activity that suggests a different level of concern. NASA has launched its largest planetary defense exercise to date, running through January 2026, using 3i Atlas as a live target for tracking and simulation. They're not shooting at it. They're not attempting to deflect it. But they're treating it as if it were a threat, refining the radar and laser tracking systems that would be needed if a similar object ever did pose a collision risk. This is being framed as an opportunity, a rare chance to test planetary defense protocols against an actual interstellar object. But it's also a dry run for a scenario nobody wants to think about. What if the next visitor isn't just passing through? What if it's aimed at us? The European Space Agency has been more forthcoming with data but equally cautious with interpretation. Their spectroscopic analysis confirms the nickel anomaly, the carbon dioxide dominance, the presence of complex organics. They've published preliminary findings that are available to the research community. But when it comes to explaining what it all means, they defer to ongoing analysis, suggesting that more data is needed before conclusions can be drawn, which is scientifically prudent but also a way of avoiding difficult questions. In China, state media has covered the flyby as a triumph of modern astronomy, a demonstration of humanity's growing ability to detect and study objects from beyond the solar system. There's pride in the fact that Chinese telescopes contributed to the observational campaign, but there's also a notable absence of speculation. The coverage sticks to facts, avoids controversy, presents 3i Atlas as an interesting scientific curiosity and nothing more, and then there's the internet, where things get really interesting. Social media platforms are ablaze with discussion, debate, and wild speculation. The hashtag JustBlueKachina is trending, a reference to Hopi prophecies about a blue star that signals the end of an age. Users are posting images of 3i Atlas blue-green coma, drawing connections to ancient myths, claiming this is the harbinger of transformation or catastrophe that was foretold. Others are analysing the heartbeat data, convinced it's encoded communication. There are threads dedicated to attempting to decode the pulse pattern as Morse code, as binary, as mathematical sequences. None of it holds up to scrutiny, but the fervour is real. People want to find a message. They need to believe there's intelligence behind the signal. Conspiracy communities are having a field day. Some claim 3i Atlas is a cover story for a classified weapons test. Others insist it's a probe sent by a breakaway civilization that left Earth millennia ago and is now returning. Still others weave it into existing narratives about government cover-ups and hidden knowledge. And underneath all of it, there's a current of genuine fear. Not panic, not hysteria, but a low-grade anxiety that something fundamental is shifting. That the universe is not as empty or as indifferent as we'd like to believe. That we might be witnessing first contact in slow motion, and we're not ready for what that means. The diversity of reactions is telling. Because 3i Atlas isn't just a scientific phenomenon, it's a cultural one. It's activating deep psychological patterns, ancient fears and hopes that have always been part of the human experience. We've always looked at the sky and wondered, are we alone? Is there something out there? And every time we see something we can't immediately explain, we project onto it. Gods, omens, visitors, threats. The object itself almost doesn't matter. What matters is what it represents in our collective imagination. And right now, 3i Atlas represents uncertainty. It represents the limits of our knowledge. It represents the possibility, however remote, that the cosmos is populated with minds and machines and messages we haven't learned to recognize yet. That possibility is exhilarating to some and terrifying to others. Because if we're not alone, then everything changes. Our place in the universe, our understanding of intelligence and consciousness, our assumptions about the future, all of it gets rewritten. But there's another reaction that's equally significant, though quieter. The reaction of scientists who are deeply uncomfortable with the ambiguity, but committed to the process of discovery. These are researchers who've spent careers studying comets, who understand the physics, who know that most anomalies have mundane explanations if you dig deep enough. They're not looking for aliens, they're looking for ice and rock and chemistry. And 3i Atlas is challenging them. It's forcing them to confront data that doesn't fit their models, and the temptation to dismiss it, to find a way to make it normal, is strong. Because accepting that this might be genuinely extraordinary means opening a door that's difficult to close. It means admitting that our catalogues and classifications might be inadequate. It means considering that we've been looking at the universe with blinders on, seeing only what we expect to see. And that's a hard thing for a scientist to admit. There's ego involved, there's professional reputation, there's the weight of decades of research that might suddenly seem incomplete. But there's also integrity, the willingness to follow the data wherever it leads, even if it leads somewhere uncomfortable. And right now, the data is leading into strange territory. The chemistry that doesn't match, the jet that shouldn't exist, the heartbeat that won't stop. These aren't going away. These are real measurements confirmed by multiple independent teams using different methodologies, which means the scientific community is going to have to choose. Do they expand their models to accommodate the anomalies, accepting that interstellar comets can be far more exotic than we realized? Or do they take seriously the possibility that Loeb keeps raising, that maybe, just maybe, we're looking at something that isn't a comet at all? That choice will define how we handle the next interstellar visitor, and the one after that. Because 3i Atlas isn't going to be the last. The detection rate suggests we should be seeing several of these objects per year once our survey capabilities improve. The Vera C. Rubin Observatory, coming online soon, will scan the sky with unprecedented depth and cadence. It will find interstellar visitors early and often. Are we going to treat each one as an anomaly to be explained away? Or are we going to approach them with genuine openness, willing to consider that the universe might surprise us? The cultural reaction to 3i Atlas, messy and contradictory as it is, reflects a hunger for that surprise. People want there to be more. They want the universe to be populated. They want to believe that the vastness isn't empty, that somewhere out there someone else is looking up at their sky and wondering the same things we wonder. And if a weird comet with impossible chemistry and a defying tail gives them an excuse to wonder, they're going to take it. The scientists can argue about spectral lines and jet mechanics. The public is already moving ahead, imagining civilizations and messages and connections across the void. Maybe they're wrong. Probably they're wrong. But maybe the willingness to imagine is as important as the rigor to verify. Because if we can't imagine possibilities beyond our current understanding, we'll never expand that understanding. We'll stay trapped in our models, refining them endlessly, but never breaking through to new paradigms. 3i Atlas, whatever it actually is, has given us permission to imagine. It's shown us that the cosmos can still surprise us, that there are objects out there behaving in ways we don't predict, carrying chemistry we just don't recognize, following trajectories we can't fully explain. And in the gap between what we know and what we observe, there's room for wonder, room for questions, room for the possibility that everything we think we understand is just the beginning. The heartbeat pulses on, the world watches and speculates, and the object continues its journey, indifferent to our theories, unconcerned with our debates, a mystery that touched our lives briefly and will soon vanish into the dark. Unless we catch it, unless we chase it down and force it to reveal its secrets, because there's still time, not much, but some, and there are people who think we should take the shot. The race is on, the clock is ticking, and the question now isn't just what 3i Atlas is, it's what we're willing to do to find out. The proposal landed on desks at NASA, ESA, and several private aerospace companies within hours of the December 19th flyby, Project Lyra. A mission architecture that's been sitting in theoretical limbo for years, waiting for exactly this scenario. An interstellar visitor close enough, slow enough, interesting enough to justify the extraordinary effort of a chase. The math is unforgiving. 3i Atlas is currently 270 million kilometers away, and adding 58 kilometers to that distance every single second. By the time you read a single sentence, it's moved another 500 kilometers. By the time you finish this paragraph, it's travelled further than the distance from New York to Los Angeles. The gap is widening exponentially, and conventional propulsion systems have no hope of closing it. But Project Lyra isn't about conventional propulsion. It's about using every trick in the orbital mechanics playbook to squeeze maximum velocity out of minimum fuel. Gravitational assists, solar sails, nuclear thermal rockets, ion drives powered by compact reactors. Technologies that exist but have never been combined in a single mission profile designed for one purpose: catching something that doesn't want to be caught. The core concept is elegant. Launch a probe toward Jupiter, not 3i Atlas. Use the gas giant's immense gravity well as a slingshot, whipping the spacecraft around at velocities that would take years to achieve through continuous thrust alone. Jupiter adds energy for free, borrowed from its orbital momentum around the Sun. You arrive at the planet moving fast, you leave moving faster, and the trajectory change points you exactly where you need to go. From there, it's a matter of endurance. The probe would coast for months, maybe years, gradually catching up to 3i Atlas as both objects hurtle through the outer solar system. Occasional course corrections, minimal thrust to maintain alignment, and then, if everything works perfectly, rendezvous at a distance where the Sun is barely brighter than the other stars, where temperatures hover near absolute zero, where instruments have to operate on battery power because solar panels are useless. That's the dream. The reality is considerably more complex. First, there's the launch window. To execute a Jupiter gravity assist efficiently, you need the planets to align properly, literally. Earth and Jupiter need to be positioned such that a spacecraft leaving Earth can reach Jupiter at the right time, from the right angle, to be flung in the direction of 3i Atlas' predicted trajectory. Those alignments happen on schedules measured in months and years, not weeks. The next optimal window opens in approximately 4 months. That gives you 4 months to design, build, test, and launch an interplanetary spacecraft carrying instruments sophisticated enough to make the entire mission worthwhile. For comparison, typical NASA missions take 5 to 10 years from concept to launch. The Mars rovers took nearly a decade. The James Webb Space Telescope took 2 decades. 4 months is insane. It's borderline impossible. But some engineers are arguing it can be done if you strip away everything non-essential and focus purely on function. Use existing hardware wherever possible. The probe doesn't need to be elegant. It doesn't need redundancy or creature comforts or the ability to phone home with high-resolution images. It needs to get there, collect data, and transmit results. That's it. A camera, a spectrometer, a magnetometer, a dust analyzer, power source, communication antenna, guidance computer. Everything else is ballast. Build it small, build it fast, launch it on the biggest rocket you can find, which in this case probably means a SpaceX Falcon Heavy or a United Launch Alliance Delta IV Heavy. Platforms that are operational, proven, and available for hire if you have the budget. Which brings us to the second problem. Money. A mission like this would cost billions. Minimum. You're talking about custom-built instruments, spacecraft assembly under compressed timelines, launch services, mission operations, and the very real possibility that despite all that expenditure, the probe fails, or the data is inconclusive, or the object turns out to be exactly what the conservatives think it is. A weird rock with unusual chemistry. No government is going to allocate that kind of funding on short notice for what many officials see as a fishing expedition based on ambiguous data. The political will doesn't exist. The bureaucratic machinery doesn't move that fast. But private entities might. And this is where the rumours get interesting. There are whispers that certain individuals, billionaires with a known interest in space exploration and the search for extraterrestrial intelligence, have had quiet conversations with aerospace engineers about feasibility. Not official contracts, not public announcements, just exploratory discussions about what it would take, what it would cost, whether it could actually be done. Names get mentioned. Elon Musk, who's already demonstrated a willingness to fund ambitious space projects out of pocket. Yuri Milner, the Russian billionaire behind breakthrough initiatives, who's poured hundreds of millions into SETI research. Jeff Bezos, whose Blue Origin has the heavy lift capability and the stated goal of expanding humanity's presence in space. Any of them could, in theory, write the check. The question is whether the potential payoff justifies the risk. Because if you spend $2 billion chasing 3i Atlas and it turns out to be a comet, you've bought yourself some interesting science but no paradigm shift. You've confirmed what most scientists already believe. But if Loeb is right, if there's even a chance he's right, then the return on investment becomes incalculable. Physical contact with extraterrestrial technology would be the most significant discovery in human history. The materials alone could revolutionize engineering. The propulsion systems, if they can be studied, might teach us physics we haven't imagined. The mere confirmation that we're not alone would reshape philosophy, religion, politics, everything. That's the gamble. Billions for a lottery ticket with unknowable odds and a potential prize beyond measure. And the clock is ticking. Every day of delay makes the mission harder. The Delta V requirements increase. The flight time extends. The already slim margins get slimmer. Within 6 months, the window closes completely. The geometry no longer works. You'd need radically different propulsion, velocities approaching relativistic speeds, technologies we don't have and won't have for decades. So the conversations are happening now. In boardrooms and private offices and encrypted video calls, engineers are running simulations, accountants are tallying costs, and somewhere, someone is making a decision about whether to pull the trigger. The European Space Agency has a mission called Comet Interceptor scheduled for launch in 2029. It's designed exactly for this purpose, a spacecraft that parks itself at a gravitationally stable Lagrange point and waits for a suitable target to appear. When a long-period comet or interstellar visitor enters the inner solar system, Comet Interceptor launches from its parking orbit, intercepts the target, and deploys multiple probes to study it from different angles. It's perfect. Except it's 4 years away. and 3i Atlas will be long gone by then, a fading speck in the outer dark beyond the reach of anything we can currently throw at it. The irony is almost painful. We designed the tool for this exact situation, but we didn't have it ready when the situation arrived. It's like installing a fire extinguisher the day after the house burns down. Useful for next time, but next time might be very different, because each interstellar visitor is unique. The next one might not be as interesting. It might be moving too fast to intercept. It might pass through a region of the solar system where our observation geometry is poor. It might show none of the anomalies that make 3i Atlas so compelling. This could be our best shot, and we're watching it slip away. But there's another angle to consider. What if we don't need to catch up to the object itself? What if we can study the trail it's leaving behind? 3i Atlas is shedding material as it moves. Gas, dust, possibly larger fragments if internal pressures cause sporadic outbursts. That material spreads out along the object's orbital path, creating a diffuse trail that extends for millions of kilometers, and unlike the nucleus, which is racing away at hyperbolic velocity, the trail is relatively stationary. It's expanding slowly, dispersing under the weak pressure of solar wind, but it's not fleeing the solar system. A sample return mission to the trail would be vastly easier than an intercept. You don't need to match velocity with a hyperbolic target. You just need to reach a point along the object's trajectory, collect material from the trail, and return it to Earth for analysis. The technology for this exists. We've done sample return missions from asteroids and comets. Japan's Hayabusa missions collected material from asteroid surfaces and brought it back to Earth. NASA's OSIRIS-REx did the same with asteroid Bennu. The techniques are proven. The challenge is adapting them to an interstellar trail, where the material density is low and the composition might be unlike anything we've handled before. But imagine what you could learn from a physical sample. Not remote spectroscopy through millions of kilometers of space, not inference and modeling, actual material in a laboratory where you can use every analytical tool we've developed. Electron microscopes to examine the structure at atomic scales, mass spectrometers to determine isotopic ratios with precision, crystallography to understand how the material formed and evolved. If there's nickel without iron, a physical sample would tell us exactly how and why. If there are exotic organics, we could identify their molecular structure definitively. If there are any artificial materials, any alloys or compounds that don't form naturally, we'd know immediately. And if the sample contains anything biological, even microbial life in a state of suspended animation preserved in ancient ice, that would answer the panspermia question once and for all. The timeline for a sample return mission is longer. You're probably looking at 5 to 7 years from authorization to Earth return. But the payoff is concrete, tangible. You bring back a piece of another star system and you study it at your leisure. Multiple research groups are actively lobbying for this approach. Papers are being written. Proposals are being drafted. The argument is that even if we can't catch 3i Atlas itself, we can catch the pieces it's leaving behind. And those pieces might tell us everything we need to know. There's precedent for this. We've studied meteorites for over a century, and they've taught us an enormous amount about the early solar system, about planet formation, about the materials that were available when Earth was young. An interstellar meteorite, a fragment of 3i Atlas that we could hold in our hands and analyze in clean rooms, would be the ultimate upgrade to that tradition. But the trail is dispersing. With every day that passes, the material spreads out, becomes more diffuse, harder to locate and collect. There's a window for this approach too, not as narrow as a direct intercept, but still finite. Within a few years, the trail will be too thin to sample effectively, so multiple timelines are running simultaneously. The immediate timeline, measured in weeks, for a decision on whether to attempt a rapid intercept using private funding and compressed development. The medium timeline, measured in months for a more conventional mission to sample the trail. And the long timeline, measured in years, for systematic study using existing and planned observatories. Each approach has advantages, each has risks, and the choice we make, collectively as a civilization, will determine how much we learn from this visitor, and how quickly we learn it. But underneath all the mission planning and engineering studies and budget discussions, there's a more fundamental question. Why are we so desperate to catch this thing? What is it about 3i Atlas that has triggered this level of urgency? The answer, uncomfortable as it might be, is that we're scared we might be missing something, that this might be the moment, the contact event, the arrival of evidence that we're not alone, and if we don't grab it now, we might never get another chance. We're haunted by Oumuamua, that first interstellar visitor that appeared and vanished before we truly understood what we were looking at. The anomalies were there. The acceleration that didn't fit simple outgassing. The weird shape, the tumbling rotation. But by the time we realized how strange it was gone, too far to study further, and the debate continues to this day. We don't want to make that mistake again. We don't want to watch 3i Atlas disappear and spend the next decade arguing about what it might have been. We want answers, definitive, unambiguous answers, and the only way to get those is to catch it. The desperation is palpable in scientific conferences, in social media discussions, in the emails flying between researchers at all hours. There's a sense that we're on the edge of something, that the universe is offering us a glimpse behind the curtain, and we're fumbling with the tools needed to pull it back. Avi Loeb is particularly vocal about this. He argues that the scientific community's resistance to the artificial hypothesis is causing us to underinvest in observation and interception. We're treating 3i Atlas like an interesting comet when we should be treating it like potential first contact. And that difference in framing leads to very different decisions about resource allocation. If it's a comet, we can afford to be patient, study it from a distance, wait for the next one, refine our models over decades. No rush. But if there's any chance it's something else, then every moment we're not chasing it is a moment we're losing irreplaceable data. Loeb's position is that we should err on the side of investigation, that the cost of a failed intercept mission is trivial compared to the cost of missing the discovery of the millennium. That scientific conservatism, which serves us well in most contexts, might be exactly the wrong approach when dealing with phenomena that don't fit established categories. The pushback from mainstream scientists is equally passionate. They argue that Loeb is letting enthusiasm override rigour, that the anomalies, while interesting, are not yet unexplainable through natural processes, that launching expensive missions based on incomplete data and speculative hypotheses is bad science and worse policy. They point out that the history of astronomy is full of anomalies that seemed inexplicable until better data and better models resolved them. Pulsar signals that were briefly thought to be alien beacons turned out to be rotating neutron stars. Fast radio bursts that seemed artificial turned out to be astrophysical phenomena. The canal structures on Mars that suggested civilization turned out to be optical illusions. Nature, they argue, is endlessly creative at producing phenomena that look designed. Snowflakes have six-fold symmetry that seems almost mathematical. Crystals form geometric patterns that look architectural. Planetary rings appear as perfect circles from a distance. None of these things are artificial, but all of them display structure and pattern that could fool an observer predisposed to see intelligence. The debate is fierce because both sides have valid points, and because the stakes are genuinely high. Make the wrong call, and you either waste resources chasing phantoms or miss the most important discovery humanity could make. Threading that needle requires judgment, and judgment, when dealing with the unknown, is always uncertain. But the decision timeline is compressing. The launch window for a Jupiter assist is approaching. The material trail is dispersing. The object itself is fading from view as it moves beyond the range of all but the largest telescopes. Within weeks, possibly days, someone is going to have to decide, chase or don't chase, commit billions to an uncertain outcome, or accept that we'll study this visitor from a distance and hope the next one is more cooperative. That decision is being made right now, in conference rooms, in private communications, in the minds of the few people with the authority and resources to make it happen. And while they deliberate, the universe continues its indifferent rotation. 3i Atlas doesn't care whether we chase it. The laws of physics don't bend to accommodate our curiosity. Time flows at 58 kilometers per second worth of distance, and that distance accumulates, whether we're ready or not. The visitor came, the visitor is leaving, and we're standing at a crossroads, trying to decide whether to wave goodbye or run after it shouting, "Wait, please, we need to know what you are." The romantic in me wants us to chase, wants us to commit every resource we have to catching this thing and forcing it to reveal its secrets, wants us to treat this like the pivotal moment it might be, and act with the urgency that recognition demands. The realist in me knows that's probably not going to happen, that the bureaucratic inertia is too strong, the scientific consensus too conservative, the risk-averse nature of institutional decision-making too entrenched, that we'll study 3i Atlas from Earth, we'll publish papers, we'll argue about models, and we'll let it go. And maybe that's fine. Maybe it is just a comet. Maybe all the anomalies will eventually resolve into exotic but natural processes. Maybe in 10 years we'll look back on this moment and smile at how excited we got over chemistry and geometry that turned out to have perfectly mundane explanations. Or maybe we'll look back with regret, with the haunting knowledge that we had a chance and didn't take it, that we were offered a gift from the cosmos and were too cautious, too conservative, too afraid of being wrong to accept it. Time will tell, but time is the one resource we can't manufacture, and it's running out faster than 3i Atlas is running away. The heartbeat continues, the data accumulates, the debates intensify, and the object speeds toward the outer darkness, indifferent to our uncertainty, unconcerned with our theories, a mystery that will soon pass beyond our reach. Unless we move, unless someone, somewhere, decides that the risk is worth taking, that the unknown is worth pursuing, that the possibility, however remote, justifies the cost. The next few weeks will answer that question, and the answer will say something important about who we are as a species, whether we're the kind of civilization that reaches for the unknown, or the kind that watches it pass by safely from a distance. Both choices are defensible, both have merit, but only one gives us a chance at the truth, and in the end that might be what matters most, not whether we're right or wrong about what 3i Atlas is, but whether we tried to find out. Now let's pull back from the immediate question of interception and look at something that's been lurking in the background of this entire discussion, the galactic context, because 3i Atlas, whatever it is, didn't just appear out of nowhere. It came from somewhere. It has a history that stretches back millions, possibly billions of years, and understanding that history might tell us as much about the object as studying it directly. Think about what it means for something to travel between stars. The distances are almost incomprehensible. The nearest star to our Sun, Proxima Centauri, is 424 light-years away. That's about 40 trillion kilometers. At 3i Atlas, current speed of 58 kilometers per second, which is actually quite fast by solar system standards, it would take over 20,000 years to cover that distance, which means if 3i Atlas came from Proxima Centauri, the nearest possible source, it's been travelling for at least 20,000 years. And that's assuming it came from the nearest star, which is statistically unlikely. Most stars are much farther away. The Milky Way is 100,000 light-years across. A random object ejected from a random star and travelling for 1 billion years might cross a significant fraction of the galaxy before happening to pass through our solar system. During that journey, the object would be exposed to conditions we can barely imagine. The interstellar medium, the space between stars, isn't empty. It's filled with gas, mostly hydrogen, at incredibly low densities. But over millions of years, those sparse atoms add up. They bombard the surface, they erode features, they deposit material. Cosmic rays, high-energy particles travelling near the speed of light, penetrate the surface and alter the chemistry at atomic scales. This is the cosmic ray processing we discussed earlier, and it's not hypothetical. We see evidence of it in meteorites that have spent time in space. The surfaces show distinctive patterns of weathering and radiation damage. Isotopic ratios get shifted. Minerals transform. The longer an object spends in interstellar space, the more processed it becomes. 3i Atlas has been travelling for a very long time, long enough that its surface chemistry might bear little resemblance to what it looked like when it formed. We're not seeing the original material. We're seeing the product of millions of years of radiation cooking, chemical alteration, and physical weathering. That makes interpretation difficult. If the chemistry is strange, is it strange because the object formed in a weird place, or strange because the journey changed it? How do you separate the formation signature from the processing signature? You can't, really, not without a reference sample, not without something to compare it to. Which is why the sample return mission becomes even more important. If we had physical material, we could analyze the damage patterns, trace the isotopic signatures, reconstruct the exposure history. We could potentially work backward from what we observed to what the object was before it left its home system. But without that, we're guessing. Educated guessing, informed by models and analogies to things we have studied, but guessing nonetheless. The trajectory offers some clues. Researchers have attempted to trace 3i Atlas's path backward through the galaxy, using its current position and velocity to extrapolate where it might have come from. This is tricky because galactic dynamics are complex. Stars move. Gravitational perturbations from passing molecular clouds or spiral arm crossings can deflect an object's trajectory over millions of years, but you can make estimates. The results suggest 3I Atlas likely originated somewhere in the general direction of the galactic centre, or possibly from a star system that's no longer where it was when the object was ejected. Remember, if this thing has been travelling for 100 million years, the stars have moved. A lot. The galactic rotation period is about 225 million years, so in 100 million years, the Sun and all nearby stars have completed nearly half an orbit around the galactic centre. You can't point at a specific star and say, it came from there with any confidence. The best you can do is narrow it down to a region of the galaxy and a time frame, and even that involves assumptions about gravitational influences we can't fully model. But the fact that it's here at all tells us something important. Interstellar objects exist. They travel between stars, and they arrive in our solar system with enough frequency that we're detecting several of them per decade now, that our survey capabilities have improved. That frequency matters, because it allows us to estimate how many of these objects are out there. How densely populated is interstellar space with rogue comets and asteroids and whatever else gets ejected from planetary systems during their chaotic formation phases? The current estimates, based on the detection rate of Oumuamua, 2I Borisov, and now 3I Atlas, suggest there might be trillions of interstellar objects in the galaxy at any given time, debris from planetary formation, kicked out by gravitational interactions with giant planets, fragments from collisions and disruptions, material that never quite accreted into planets and instead ended up on ejection trajectories. The galaxy is full of this stuff. We're just starting to see it because our telescopes have finally gotten good enough. And that raises a fascinating question. If interstellar space is littered with the debris of planetary formation, if every star system is constantly shedding material that then wanders the galaxy for billions of years, what are the implications for panspermia? Panspermia is the hypothesis that life doesn't arise independently on every planet where it appears. Instead, it travels. Microorganisms, or at least the chemical building blocks for life, hitch rides on comets and asteroids. They survive the journey in a state of dormancy, frozen in ice, protected from radiation by layers of rock. And when one of these travelers happens to crash into a planet with the right conditions, liquid water, organic chemistry, stable climate, the seeds sprout. It's a compelling idea because it explains some puzzling observations. Life appeared on Earth remarkably quickly after the planet cooled enough to support it. The oldest fossils date to within a few 100 million years of Earth's formation. That's a very short time for chemistry to bootstrap itself from simple molecules to self-replicating organisms. But if life didn't start from scratch on Earth, if it was seeded from elsewhere, then the timing makes more sense. You're not waiting for a biogenesis to happen here. You're just waiting for the right delivery. 3I Atlas is carrying organic molecules. The spectroscopic data confirms methanol, carbon dioxide, complex carbon compounds. These are precursors, the raw materials from which life could potentially emerge given the right conditions. As it passed through our solar system, it shed some of that material. Not much, a tiny fraction of its mass. But that material is now part of our neighbourhood. It's in the solar wind. Some of it might eventually drift into planetary atmospheres. A few molecules might even make it to Earth's surface. We're being pollinated. Gently, diffusely, with chemistry from another star system. And if 3I Atlas is typical, if most interstellar visitors carry similar organic cargo, then this process has been happening for billions of years. Earth has been receiving a steady drizzle of interstellar organics, delivered by comets and asteroids that pass through or occasionally impact. Did any of that material contribute to the origin of life here? We don't know. It's possible. It's also possible that life emerged entirely from Earth's own chemistry, and the interstellar contribution was negligible. But the mechanism exists. The delivery system is real. And if it works here, it works everywhere. Every planet in the galaxy with the right conditions is receiving the same deliveries, the same chemical seeding, the same potential raw materials for biology, which means life, if it can start at all, might not be rare. It might be common. Because the ingredients are being distributed across the galaxy by a natural network of interstellar messengers, comets and asteroids carrying the building blocks of biology from star to star, spreading the potential for life wherever they go. This is the optimistic interpretation. The idea that 3i Atlas, regardless of whether it's natural or artificial, is part of a galactic ecosystem, a system where material and chemistry and potentially even biology circulate, ensuring that wherever conditions are right, life has a chance to take hold. But there's a darker interpretation too, one that's harder to dismiss once you've considered the anomalies we've been discussing. What if the delivery is intentional, not in the sense of conscious direction, but in the sense of design? What if civilizations, advanced technological civilizations, use interstellar objects as vectors? What if they seed comets and asteroids with whatever they want to distribute, whether it's microbes or nanomachines or information encoded in DNA, and then send those objects on trajectories that will eventually cross paths with promising star systems? It's a slow process, glacially slow, but it's patient, and it doesn't require faster-than-light travel or enormous energy expenditures. You just need to nudge objects onto the right trajectories and wait. Over millions of years, they'll spread across the galaxy, delivering their cargo to any planet that happens to be in the way. This is directed panspermia, the hypothesis that life on Earth wasn't an accident, but a deliberate act of seeding by an older civilization. It's speculative, it's controversial, but it's not scientifically impossible, and if 3i Atlas is showing signs of design, if the trajectory is too precise, and the chemistry too refined and the structure too organized, then maybe what we're witnessing isn't first contact in the traditional sense. Maybe it's delivery, a package from an older civilization, sent before humans existed, before Earth had complex life, before the Sun had planets, sent as part of a long-term galactic project to ensure that life takes root wherever it can. Francis Crick, the co-discoverer of DNA structure, took directed panspermia seriously enough to co-author a paper on it. He argued that the genetic code is too universal, too optimized, to have arisen by chance on a single planet, that it might be an engineered system, distributed across the galaxy by a civilization trying to seed as many worlds as possible with the same basic biochemistry. That paper was written in 1973, and it's still debated. Most scientists dismiss it as unnecessary. Evolution can explain the genetic code without invoking ancient astronauts. But the argument hasn't been definitively refuted either, and now we have an interstellar visitor carrying organics, exhibiting anomalies, following a trajectory that brought it past multiple planets, including Earth. If you were designing a panspermia system, isn't that exactly what you'd want? Objects that pass through star systems on safe trajectories, shedding material as they go, maximizing the chance that some of that material lands on habitable worlds? I'm not saying this is what's happening. I'm saying the hypothesis exists, and 3i Atlas fits the profile disturbingly well. The trajectory is particularly interesting from this perspective. It came into the solar system from above the ecliptic plane, the flat disk where the planets orbit. It passed by Jupiter, which is massive enough to have captured it if the geometry had been slightly different. It skimmed past Mars, it flew by Venus, it came within 168 million miles of Earth. That path took it past 4 planets, 3 of them in the habitable zone or close to it. If you were trying to maximize exposure to potentially life-bearing worlds, you couldn't ask for a better route. And it did all this without colliding, without being captured, without fragmenting from tidal stresses. It threaded the needle. Perfectly. Coincidence? Probably. The solar system is mostly empty space. Most trajectories that enter will pass through without hitting anything. That's just probability. But the precision is striking, especially when combined with all the other oddities. The heartbeat, the nickel, the collimated jet, the stable trajectory. Each one individually is explainable, but together they form a pattern. And humans are pattern recognition machines. We see faces in clouds and conspiracies in coincidences. We're wired to find meaning even when there isn't any. So maybe the pattern is real, or maybe we're just doing what humans do, imposing narrative on randomness because we can't tolerate the idea that the universe is fundamentally indifferent. The truth is probably somewhere in between. 3i Atlas is almost certainly natural. The chemistry is weird but not impossible. The trajectory is lucky but not miraculous. The anomalies are puzzling but will likely resolve with better data and better models, but that almost certainly is doing a lot of work. Because certainty in science is always provisional. And when you're dealing with a phenomenon you've never encountered before, from an origin you can't verify, behaving in ways you didn't predict, The margin for error is larger than usual. We don't know what we don't know. And 3i Atlas is teaching us forcefully that the list of things we don't know is longer than we thought. The galactic context expands the frame. It reminds us that our solar system isn't isolated. We're part of a larger ecosystem, a gravitational and chemical web that connects every star in the galaxy over timescales measured in millions and billions of years. Material circulates, chemistry spreads, and if intelligence exists elsewhere, then ideas and technologies and perhaps even biology circulate too. 3i Atlas is a node in that network, a visitor from another part of the web. And whether it's a random traveller or a deliberate messenger, it's brought with it information about places and processes we can't access any other way. The chemistry it carries formed in a stellar system with different conditions than ours. The structure it displays was shaped by a journey through interstellar space that we can't replicate. The trajectory it follows was determined by gravitational interactions light years away and millions of years ago. All of that is encoded in the data we're collecting. The spectra, the images, the orbital parameters. Every measurement is a piece of a story that began before humans existed and will continue long after we're gone. Our job is to read that story, to extract meaning from the signals, to understand what we're seeing and why it matters. And to do that, we need to stay open. We need to resist the temptation to force the data into comfortable categories. We need to let the object tell us what it is instead of telling it what we think it should be. That's harder than it sounds, because our brains crave resolution. We want answers. Definitive, unambiguous answers. And when the data doesn't provide them, we invent them. We fill in the gaps with assumptions and extrapolations and best guesses. But 3i Atlas is teaching us to sit with uncertainty, to accept that some questions don't have answers yet, to be patient while the data accumulates and the models improve. The visitor is leaving, the window is closing. But the story is far from over, because every object like this that we detect, every interstellar traveller that passes through our neighbourhood, adds to the catalogue, adds to our understanding of what's out there and how it behaves. 3i Atlas is one data point. Oumuamua was another. 2i, Borisov was a third. The next one will be the fourth, and somewhere around the 10th or 20th or 50th, we'll start to see patterns. We'll start to understand what's normal for interstellar objects and what's genuinely anomalous. And maybe, just maybe, one of them will be so obviously artificial that even the conservatives can't explain it away. So clearly designed that the debate ends and a new era begins. Or maybe they'll all be rocks, weird rocks with unusual chemistry and surprising trajectories, but rocks nonetheless. And we'll accept that the galaxy, while full of matter and motion, is empty of minds other than our own. Both futures are possible. Both are consistent with what we know. And 3i Atlas, speeding away at 58 kilometers per second, isn't telling us which one we're living in. Not yet. But it's given us clues, breadcrumbs, hints that something more might be possible. And those hints are enough to keep us looking, enough to keep us questioning, enough to keep us reaching for the unknown even when the unknown refuses to reach back. The heartbeat fades, the distance grows, the data thins, but the impact remains. 3i Atlas has changed us, has changed how we think about interstellar visitors, has changed the questions we ask and the possibilities we consider, and that might be the most important legacy of all. Not what the object is, but what it's taught us about ourselves, about our curiosity, our fear, our desperate hope that somewhere out there we're not alone. The visitor came bearing mysteries, and mysteries unanswered have a way of reshaping the minds that encounter them. We're different now than we were before July 2025, when a survey telescope in Hawaii first detected a moving object that didn't belong. We're more uncertain, more humble, more aware of how much we still don't understand about the cosmos we inhabit. And maybe that's exactly what we needed. A reminder that for all our telescopes and theories and mathematical models, the universe still has surprises, still has secrets, still has the capacity to show us things we weren't expecting and challenge us to rise to the occasion. 3i Atlas is gone, or will be soon. But the questions it raised will remain, will haunt us, will drive us to build better instruments and launch bolder missions and think harder about what we're looking for and why. Because the next visitor is coming, maybe in 5 years, maybe in 5 months, and when it arrives, we need to be ready, ready to observe, ready to analyze, ready to chase if necessary, ready to face the possibility that the universe is stranger, fuller, more alive than we've allowed ourselves to imagine. The chase might be over, but the hunt has just begun. The diplomatic channels opened quietly on December 21st, 2 days after closest approach. Not press conferences, not public statements. Classified communications between space agencies, defense departments, and a handful of research institutions that have clearance to discuss objects that might, under certain interpretations, represent security concerns. Because while the public debate centers on whether 3I Atlas is a comet or something else, there's a parallel conversation happening in secured facilities about what it means either way. If it's natural, it's a reminder that our detection systems work, that we can spot interstellar visitors early enough to study them, and that the next one might not be on such a safe trajectory. If it's artificial, then we need protocols we don't currently have for first contact scenarios that don't involve communication or intent we can verify. The United States Space Force has been tracking 3I Atlas since discovery, not just as a scientific curiosity, but as an exercise in rapid response. Their radar systems, designed to track satellites and debris in Earth orbit, were pushed to their limits trying to maintain lock on an object moving hyperbolic velocity at interplanetary distances. They succeeded, which is itself notable. It means the infrastructure exists to track threats coming from deep space, not just objects already in near-Earth orbit. Russia's response, beyond Putin's awkward joke, has been characteristically opaque. Their space agency released minimal data. Their telescopes observed the flyby, but the analysis remains internal. Some Western researchers suspect they're seeing the same anomalies everyone else is seeing and don't want to be the first to publicly suggest those anomalies might be significant. Plausible deniability. Let someone else make the controversial claims. China has been more forthcoming with observational data, but equally cautious with interpretation. Their statements emphasize scientific cooperation, the importance of international coordination in studying rare events, and the value of shared data. But there's calculation underneath. They're positioning themselves as responsible actors in space, contributing to humanity's collective knowledge, while avoiding speculation that could be embarrassing if proven wrong. The European Space Agency has arguably been the most transparent. Their scientists are publishing preliminary findings, sharing spectra, discussing the anomalies openly in academic contexts. But even they're careful. Papers describe unusual chemical ratios and unexpected photometric behavior without using words like artificial or technological. The language is precise, measured, designed to communicate without inflaming. And beneath all this diplomatic maneuvering, there's a recognition that 3I Atlas has exposed a gap in our planetary defense framework. We have protocols for asteroids. We have impact probability calculations and deflection mission designs. We've tested kinetic impactors on real asteroids to verify we can change their trajectories if needed. But all of that assumes natural objects following predictable orbits, objects that don't maneuver, objects that don't make course corrections. If something enters the solar system that can steer, that can change its trajectory in ways we can't predict, our entire defense paradigm breaks down. You can't deflect an object that's actively avoiding you. You can't calculate impact probabilities for something that's choosing its own path. The math fails, the models fail, and you're left with uncertainty that no amount of observation can resolve until you see what the object actually does. NASA's planetary defense exercise, the one using 3I Atlas as a live target, is partly about this scenario. They're not preparing for 3I Atlas specifically. They're preparing for the next object that shows similar characteristics, the one that might not pass safely, the one that might demonstrate course correction capability while headed toward Earth instead of away. How do you respond to that? Do you attempt communication? Do you treat it as a threat and develop weapon systems capable of destroying it? Do you evacuate and hope it's just passing through? These aren't hypothetical questions anymore. 3I Atlas has made them concrete, and the answers aren't obvious. There's also the question of what information gets shared with the public. Right now, most of the detailed anomalies are buried in technical papers that only specialists read. The mainstream media coverage has been superficial. An interstellar comet flew by. It was safe. Scientists are studying it, nothing to worry about. But the specialist community is having a very different conversation. In academic journals and private communications and secure video conferences, researchers are discussing data that doesn't fit, chemistry that's wrong, physics that's broken, trajectories that look designed. Should that conversation be public? Should ordinary people know that there's genuine scientific debate about whether we've just been visited by technology from another civilization? Or would that create panic, confusion, conspiracy theories that undermine trust in institutions? It's a delicate balance. Transparency is important, but so is responsible communication. And when the data is ambiguous, when even experts disagree about interpretation, throwing that uncertainty at a public that wants clear answers can do more harm than good. So the information trickles out slowly. Papers get published, conferences happen, journalists with science backgrounds start asking harder questions, and gradually the story shifts from interesting comet to mysterious object to we're not entirely sure what we saw. That shift is happening now, in real time. The narrative is evolving as the data accumulates and the implications sink in, and 3i Atlas, indifferent to our narratives and our politics and our careful diplomatic language, continues racing away, 58 kilometers per second, every second, without pause, without deviation, following a trajectory that's either the product of billion-year-old gravitational interactions or something else entirely. The observational window is closing faster than anyone wants to admit. Already the object has dimmed to the point where only the largest telescopes can track it reliably. The Hubble Space Telescope is still collecting data, but the signal-to-noise ratio is degrading. The James Webb Space Telescope, with its infrared sensitivity, can see it for a bit longer, but even JWST has limits. Within weeks, 3i Atlas will drop below detection thresholds. It will still be out there, still moving, still carrying its secrets. But we won't be able to see it anymore. It will fade into the background noise of distant stars and dust and cosmic radiation, and then it will be gone. Truly gone. A memory, a data set, a mystery that future generations might solve or might argue about forever. The Comet Interceptor mission, scheduled for 2029, will be ready for the next visitor, assuming there is a next visitor, assuming it's as interesting as this one, assuming we get lucky again. But luck isn't a strategy, and waiting for opportunities to arrive on their own timescale isn't how you build systematic knowledge. Which is why some researchers are pushing for a dedicated interstellar object early warning network, a system of telescopes specifically designed to detect these visitors as early as possible, ideally while they're still in the outer solar system, before they swing past the sun and accelerate away. The technology exists, wide-field survey telescopes scanning the sky nightly, looking for anything that moves. Machine learning algorithms trained to distinguish interstellar visitors from asteroids and comets based on trajectory and velocity, automated alert systems that notify researchers immediately when something interesting appears. The Vera C. Rubin Observatory will provide much of this capability once it's operational, but there's talk of supplementing it with dedicated assets, smaller telescopes in strategic locations, space-based platforms that can maintain continuous watch without atmospheric interference, a coordinated network that ensures nothing slips through unnoticed. Because if interstellar visitors are arriving at the rate the statistics suggest, several per year, then we're missing most of them. We're catching the bright ones, the close ones, the ones that happen to cross our field of view at the right time. But for every 3i Atlas we detect, there might be 10 more that pass through unobserved. Building the infrastructure to catch all of them, or at least most of them, is an investment in knowledge, in preparedness, in ensuring that when the genuinely significant visitor arrives, the one that's unambiguously artificial or poses a real threat, we see it coming with enough advance notice to respond. That investment is being debated now. Budget proposals, international partnerships, technical specifications, the usual bureaucratic machinery that turns ideas into reality over timescales measured in years and decades. But 3i Atlas has provided urgency, has demonstrated that these objects exist, that they exhibit unexpected behavior, and that our current capabilities are barely adequate for studying them. The next one needs to be different. We need to be ready. Not scrambling to observe, not arguing about whether to launch an intercept mission while the window closes. Ready, with hardware in place and protocols established and the political will to act. Whether that happens depends on choices being made right now. Choices about funding and priorities and how seriously we take the possibility that the universe is more populated, more active, more interesting than our comfortable models suggest. Meanwhile, the scientific analysis continues. Researchers are still processing data from the flyby, still refining measurements, still running models to see which interpretation best fits the observations. The heartbeat signal has been confirmed beyond doubt. Multiple independent observations show the same periodic variation in brightness. The period is approximately 7.3 hours, which suggests that's the rotation period of the nucleus, or at least one component of its rotation, if it's tumbling on multiple axes. The amplitude of the variation is larger than you'd expect from simple rotation of an irregular body. It implies significant asymmetry. Either the shape is very elongated, like a cigar or a dumbbell, or there are discrete features on the surface that reflect light very differently from each other. Attempts to model the shape from the light curve have produced ambiguous results. The data is consistent with several different geometries: an elongated ellipsoid rotating end over end, a contact binary, two objects touching or orbiting each other very closely, a single body with high albedo patches alternating with dark regions. Without resolved imaging, you can't distinguish between these possibilities definitively. But each possibility has implications. An elongated shape might indicate tidal disruption in the object's past. A contact binary suggests a gentle collision or capture event. Albedo variations could mean compositional heterogeneity, or surface features that form through processes we don't understand. The nickel signature has been scrutinized exhaustively. Multiple spectrometers on different telescopes all show the same emission lines. It's not an artifact. It's not instrumental error. There is nickel vapor in the coma of 3I Atlas, and the ratio to iron is anomalous compared to everything else we've studied. One research group has proposed a model involving differentiation and selective volatilization. They suggest the object might be a fragment of a differentiated planetesimal that was exposed to intense heating, perhaps from a stellar flare or close approach to a hot star. The heating vaporized preferentially volatile metals like iron while leaving more refractory nickel behind. Then, when the object cooled and later entered our solar system, the nickel sublimates before iron because the surface composition has been altered. It's plausible, complicated, requiring several low-probability events to happen in sequence, but not impossible, and it avoids invoking anything artificial. Another group counters that the heating required to vaporize iron selectively would also vaporize nickel and most other materials, that you can't fine-tune stellar heating to that degree. That the proposed scenario requires such specific conditions it's effectively arguing for a miracle. The debate will continue, papers will be written, rebuttals will be published, and the community will slowly converge on a consensus, or it won't, and the question will remain open for future data to resolve. The antitail has been modelled extensively. The best natural explanation involves large dust grains ejected sunward due to anisotropic outgassing. If the nucleus has an active vent that happens to point toward the sun at certain rotation phases, and if the material ejected is dominated by massive particles rather than fine dust, those particles could travel sunward for a while before solar radiation pressure and gravity balance out, and they start falling back or dispersing. The collimation, the narrow beam structure, is explained as a geometric effect. We're seeing the densest part of a broader spray, the core of the jet where particle density is highest. The apparent column isn't actually that narrow, it just looks that way because the fainter, more diffuse material around it is below our detection threshold. Again, plausible. Again, requiring specific conditions. But not impossible. Loeb has published a counter-analysis arguing that the collimation is too perfect, the stability too consistent, the geometry too convenient, that natural jets should be messier, more chaotic, more time variable, that we're seeing something maintained, something controlled, something that looks like engineering because it is engineering. His paper has generated significant pushback. Other scientists have accused him of cherry-picking data and ignoring observations that contradict his thesis. He's countered that they're dismissing anomalies without adequate explanation and clinging to natural models out of ideology rather than evidence. The tone has become heated, personal, which is unfortunate because the science should stand on its own regardless of who's presenting it. But humans are humans, and egos and reputations get involved, and suddenly you have factions instead of collaborators. Beneath the acrimony, though, there's genuine uncertainty. Nobody knows for sure what 3I Atlas is. The data supports multiple interpretations, and until we get better data, either from closer observation of this object or from studying similar objects in the future, the ambiguity will persist. What's clear is that 3i Atlas doesn't fit neatly into our existing categories. It's not a typical comet. It's not a typical asteroid. It's something else. Something from outside our solar system, formed under different conditions, shaped by a different history. Whether that makes it natural or artificial is the question we can't answer yet. But it's forced us to expand our thinking, to consider possibilities we'd previously dismissed, to accept that the universe is larger and stranger than our provincial experience suggests, and that expansion, that stretching of our conceptual boundaries, might be the most valuable thing 3i Atlas leaves behind, because the next visitor is coming, maybe in months, maybe in years, but it's coming, and when it does, we'll be a little bit wiser, a little bit more prepared, a little bit less certain that we know what we're looking at. The humility is important. Science advances not just through discovery, but through the recognition of ignorance, through admitting what we don't know and using that admission as motivation to look harder, think deeper, question more rigorously. 3i Atlas is teaching us humility, teaching us that 8 years of studying interstellar objects isn't enough to build a complete taxonomy, that 3 data points don't constitute a robust sample, that every new visitor will challenge us in ways we can't predict. And maybe, just maybe, teaching us that the universe is populated with wonders we haven't imagined yet, that the space between stars isn't empty, but filled with travelers and messengers and artifacts from civilizations we'll never meet, but whose presence we can detect if we're paying attention. That last possibility is the one that keeps people up at night, not because it's likely, but because it's possible. And possibility, once acknowledged, is difficult to ignore. The scientific method demands skepticism. Extraordinary claims require extraordinary evidence. We default to natural explanations because they are almost always correct, and invoking the extraordinary without justification is bad practice. But the method also demands openness, willingness to follow data wherever it leads, resistance to dogma that prevents consideration of legitimate hypotheses. The tension between skepticism and openness is productive when it's balanced. It keeps us honest, prevents both excessive credulity and excessive dismissiveness. With 3i Atlas, that balance is being tested. The skeptics are right to demand better evidence before accepting artificial origin. The advocates are right to insist that anomalies be taken seriously, rather than explained away with increasingly convoluted natural scenarios. Both sides are doing their jobs, and the friction between them is generating heat, yes, but also light, better observations, refined models, deeper analysis. That's how science is supposed to work, not through consensus achieved by suppressing dissent, but through debate that sharpens arguments and reveals weaknesses in reasoning. The ultimate arbiter will be data. More data, better data. Data from the next interstellar visitor and the one after that. Data from sample return missions that bring physical material back to Earth for analysis. Data from spacecraft intercepts that get close enough to resolve surface features and measure magnetic fields and detect emissions we can't see from millions of kilometers away. That data is coming. Not fast enough for those of us impatient to know the answers, but inevitably. Because the infrastructure is being built, the missions are being planned, the technology is improving. Within a decade, we'll have observatories that can detect Earth-sized interstellar objects instead of just the big ones. We'll have rapid response spacecraft parked at Lagrange points, ready to intercept targets of opportunity. We'll have sample return capability that can reach out to the asteroid belt and beyond. And when those tools come online, the trickle of interstellar discoveries will become a flood. We'll be cataloguing dozens of these objects per year. We'll start to see patterns. We'll understand what's common and what's rare. We'll build the statistical foundation needed to say definitively whether 3i Atlas is an outlier or a representative sample. Until then, we wait, and we watch, and we argue about what we're seeing. The heartbeat fades as 3i Atlas recedes. The signal-to-noise ratio degrades. The telescopes strain to maintain lock on an object that's now just barely brighter than the background stars. Soon it will be indistinguishable, lost in the noise, gone. But the legacy remains. The data collected during its brief visit will be analysed for years. Students will write dissertations on it. Papers will cite it. Future missions will use it as a baseline for comparison, and somewhere, in a database, the full record will be preserved. Every spectrum, every image, every measurement, waiting for the insight that makes sense of it all, waiting for the context that comes from studying the next 10 or 20 or 100 interstellar visitors, because that's how understanding accumulates, not in dramatic breakthroughs, but in patient accumulation of evidence, in comparing and contrasting, in finding the patterns that emerge only when you have enough data points. 3i Atlas is a data point, an important one, a strange one, a challenging one, but ultimately just one. The story it's part of is larger, the story of humanity reaching beyond Earth, of developing the capability to detect and study objects from other star systems, of slowly, incrementally expanding our understanding of the galaxy we inhabit. That story is still being written. 3i Atlas is a chapter, a memorable chapter, full of mystery and debate and unanswered questions, but not the conclusion, not even close. The conclusion comes when we've studied enough of these visitors to truly understand them, when we've launched missions that bring back samples, when we've resolved the ambiguities and answered the questions and either confirmed or definitively ruled out the possibility that some of them are artificial. That day is coming, not tomorrow, not next year, but within the lifetime of people reading this, within the span of careers now beginning, within a time frame where the answers will matter to us personally, not just to some distant future generation. And when that day comes, when we finally know what 3i Atlas was, we'll look back on this moment with clarity. We'll see how the data fit together. We'll understand why some interpretations were right and others were wrong. We'll recognize the clues we missed and the assumptions that led us astray. But we'll also recognize something else, that the uncertainty was necessary, that not knowing forced us to think harder, observe more carefully, question more deeply, that the mystery was the engine driving discovery. Because if 3i Atlas had been obviously a comet, clearly natural, easily explained, we would have catalogued it and moved on. We wouldn't have mobilized international observation campaigns. We wouldn't have debated artificial origin. We wouldn't have pushed our instruments to their limits trying to extract every bit of information possible. The strangeness demanded attention, demanded resources, demanded our best efforts, and in responding to that demand, we've advanced the field, built new capabilities, established new partnerships, expanded our conceptual frameworks. That's the gift 3i Atlas gave us. Not answers. Questions. Better questions than we were asking before it arrived. Questions about what's possible, about what exists beyond our solar system, about whether we're truly alone or sharing the galaxy with others who build and explore and send emissaries across the void. Those questions will outlive the object that inspired them, will drive research for decades, will shape how we approach future visitors and how we prepare for the possibilities they represent. So as 3i Atlas fades from view, as the observations end and the data analysis shifts from real-time to archival, we're not losing anything essential. The object itself was never the point. The point was what it made us see, what it made us consider, what it made us become. We're different now, more aware of the galaxy's complexity, more humble about our knowledge, more curious about what else might be out there, and that difference, that transformation, is permanent. The visitor came, the visitor challenged us, the visitor left, but we remain, changed, expanded, ready for what comes next. The heartbeat has stopped, not because the object stopped pulsing, but because we can't hear it anymore. The signal has dropped below our detection threshold. 3i Atlas is still out there, still rotating, still shedding gas and dust as it races toward the outer solar system, but from our perspective, it's gone silent. The last confirmed observation came from the James Webb Space Telescope on January 4, 2026. A faint infrared signature, barely distinguishable from background noise. The analysis took days to confirm. By the time researchers were certain they'd actually detected the object and not just random fluctuations in the data, the window had closed. Subsequent observations failed to relocate it. 3i Atlas has passed beyond our reach. The final trajectory calculations place it on a path that will take it past Neptune's orbit sometime in late 2026. After that, it enters the realm of the trans-Neptunian objects, the scattered disk, the innermost edges of the Oort cloud, regions we can barely observe even when we know exactly where to look. By 2027, it will be functionally undetectable with current technology, a ghost, a memory, a set of measurements and spectra that will be debated and analysed for generations. The scientific community is already pivoting. Focus is shifting from 3i Atlas specifically to the broader question of interstellar visitor detection and characterization. How do we improve our survey capabilities? How do we develop rapid response protocols? How do we prepare for the next one? NASA has announced funding for an interstellar object working group, a formal structure bringing together researchers from multiple institutions to coordinate observation strategies, share data, and develop standardized analysis techniques. The goal is to avoid the chaos of 3i Atlas D, where different teams were using different methods and coming to conflicting conclusions. ESA is accelerating the Comet interceptor timeline. The mission is still scheduled for 2029, but they're exploring options to have preliminary hardware ready earlier in case an opportunity arises. The spacecraft would still be parked at a Lagrange point, but the launch readiness would be improved. And private companies, those rumoured conversations about rapid intercept missions, have gone quiet. Either the funding didn't materialise or the feasibility studies came back negative. Either way, there will be no chase, no dramatic last-minute attempt to catch 3i Atlas before it escapes. We let it go. That decision, or non-decision, will be analysed for years. Was it the right call? Should we have tried? Could a billionaire-funded mission have succeeded if someone had been willing to take the risk? We'll never know. The window closed, the opportunity passed, and now we live with the uncertainty of what we might have found if we'd been bolder. But there's wisdom in restraint too, in not throwing resources at every anomaly, in waiting for better data before committing to expensive, uncertain endeavours. The conservative approach preserved resources for the next opportunity, avoided the political fallout of a failed intercept mission, maintained institutional credibility by not chasing after hypotheses that might prove embarrassing. Those are real considerations, real values, and they influenced the decision-making in ways that were probably inevitable given the structures and incentives of modern space science. But the regret lingers, the what-if, the knowledge that we had a chance and didn't take it. And underneath that regret is a deeper question. Are we as a civilization capable of responding to the truly unexpected? Or are we so bound by protocol and risk aversion and bureaucratic inertia that we can only react to threats we've already imagined? 3i Atlas wasn't a threat. It was an opportunity, an invitation to engage with the unknown, and we declined, politely, cautiously, reasonably, but still. We declined. The next visitor won't be identical. It might be bigger or smaller, faster or slower, stranger or more mundane. But whatever it is, we'll have learned from this experience. We'll know what data to prioritize. We'll know what questions to ask. We'll know what capabilities we need and don't have. That knowledge is valuable. That learning is real. And it came from watching 3i Atlas slip away. So maybe the decision was right. Maybe letting this one go was the price of being ready for the next one. Maybe the lesson was more important than the intercept. Or maybe we're rationalizing. Making ourselves feel better about a missed opportunity by pretending it was all part of the plan. Time will tell. The next interstellar visitor will tell. Because if it's as strange as 3i Atlas, if it exhibits the same kinds of anomalies, we'll have a choice to make. Again. And this time, the decision will be informed by what we learned here. Will we be bolder, more decisive, more willing to take risks? Or will we watch the next one fade away too, always waiting for better data, better opportunities, better certainty before we act? The pattern we establish now will define how humanity engages with interstellar phenomena for decades. 3i Atlas is the test case, the precedent, the example future missions will reference when arguing for or against bold action. And what we've established is caution, observation over intervention, study over pursuit, safety over discovery. That's not inherently wrong, but it's a choice, and choices have consequences. The data from 3i Atlas will be valuable regardless. The chemistry, the trajectory, the photometric behavior, all of it adds to our knowledge base. All of it helps us understand what interstellar objects are and how they behave. But the sample we wanted, the close-up images, the in-situ measurements, those are lost. We'll never know what the surface actually looked like. We'll never measure the magnetic field directly. We'll never sample the outgassing in real time with instruments close enough to detect components that are invisible from Earth. Those unknowns will haunt us, will appear in papers as limitations, will be cited whenever someone argues we need better interception capability. And maybe that's enough. Maybe the haunting will drive the next generation of missions. Maybe the regret will fund the infrastructure we need. Or maybe 3i Atlas will fade from public consciousness. Become a footnote, a trivia question. The third interstellar object, after Oumuamua and 2i Borisov, before the one that eventually proves definitively interesting. Either way, the object itself is gone, beyond recall, beyond reach. The sky is darker for its absence. The mystery remains unsolved, and we're left with data, debate, and the lingering question of what we missed. But life continues. Research continues. The search continues. Because 3i Atlas taught us one thing beyond doubt. They're out there. Interstellar visitors, objects from other star systems passing through ours, carrying information about places we'll never reach. They arrive more frequently than we thought. They're stranger than we expected. And they challenge us in ways we're still learning to handle. The galaxy is full of them, full of travelers and wanderers and refugees from stellar systems that formed and evolved and sometimes died long before our sun ignited. And they're coming here, not invading, not communicating, just passing through, following trajectories determined by ancient gravitational interactions, indifferent to whether we notice them or understand them or learn from them. But we do notice. We do try to understand. We do learn. And with each visitor we get a little bit better at it. 3i Atlas was our teacher. Difficult, enigmatic, frustrating, but valuable. The lessons it taught will shape how we approach the next one, and the next, and the one after that. Until eventually, maybe, we encounter one that's so obviously artificial that even the skeptics can't explain it away. Or until we've studied enough of them to definitively rule out artificiality and accept that the galaxy, while full of wonders, is empty of minds other than our own. Either answer would be closure. Either answer would let us move on from the uncertainty. But I suspect we won't get closure. Not soon. Not cleanly. I suspect the ambiguity will persist, that each new visitor will bring new anomalies that fit uncomfortably into our categories, that we'll continue debating natural versus artificial, known physics versus unknown mechanisms, coincidence versus design, and maybe that's appropriate. Maybe the universe doesn't owe us clarity. Maybe the lesson is learning to live with mystery, learning to operate despite uncertainty, learning to keep searching even when the answers remain elusive. 3i Atlas is gone. The heartbeat has faded. The data is archived. But the search continues. The wonder remains. And the next visitor is already out there, somewhere in the dark between stars, on a trajectory that will eventually bring it within range of our instruments and our questions, and our desperate hope that this time, maybe, we'll finally understand. The sky is patient. The galaxy is vast. And somewhere out there, racing toward us at speeds we can barely imagine, something else is coming. Something that might be a rock, or might be something more. We'll be watching. We'll be ready. And when it arrives, we'll face the same questions we faced with 3i Atlas. The same uncertainties, the same choice between caution and boldness. But we'll face them with experience, with knowledge earned from this encounter, with the understanding that the universe is stranger than we knew, and that our models are provisional, and that certainty is a luxury we can't always afford. 3i Atlas taught us that, taught us humility, taught us wonder, and in the end, that might be the most important lesson of all. The visitor came, the visitor left, and we remain, changed, curious, waiting for what comes next. The heartbeat of 3i Atlas has stopped. But the heartbeat of discovery continues, and that rhythm, that pulse of human curiosity reaching out into the cosmos, that will never fade, as long as we look up, as long as we question, as long as we're willing to face the unknown with open eyes and uncertain hearts. The story of 3i Atlas is over. The story of humanity's encounter with the interstellar unknown has only just begun.